Hello and welcome to another digital design class. In the previous class, we started with the registers and counters. Registers and counters are a type of sequential logic circuits. They are built out of flip-flops, and you can put these flip-flops in series or in parallel to be able to connect them to be able to create a small memory. A flip-flop can store 1 bit. You can add 4 of these flip-flops to create a 4-bit register. We have different types of registers, such as the shift registers, which are used to shift a binary digit to left or right. These shift registers, I already put one, and I solved the practice for them, are left shift registers or shift left registers and shift right registers. Today we will continue with the registers. We will continue with counters, different type of counters, such as BCD counters and Johnson counters if we have time for that. And hopefully we can conclude the registers and counters. Now, in the previous class, we learned about one type of registers. Today we're going to learn universal shift registers. So what is a universal shift register? A universal shift register is a register that could shift both to the left and the right, and it could also store data as well. Let me put it on a slide check, and I think it's going to be sorry, went from the beginning for some reason. Now, a universal shift registers has some capabilities. You can control the direction of the shift register. It could be a shift right control system or a shift left system. You can clear all the memory on the register at once by setting the control of the register to 0. A universal shift register has n input lines. It has a clock input to synchronize the input outputs. It also has a parallel load control, meaning you can feed the data all at once. Imagine you have an 8-bit register. You can feed all 8 bits at once. In the serial register, you have to do the bits one by one at a time in each clock. It has n parallel output lines, and it has a shift control as well. This is an example of a universal shift register. So we have S1 and S2 connected to these multiplexers. These are important ones. Let me bring my pen. Now, these two control the direction of the shift register and control the shift register and in a way that it dictates what the shift register should do and how should it operate. We have serial inputs for the shift register as well, and we have the parallel inputs. So we can give it both serial inputs for a shift right system, or we can give it serial input for a shift left. So we can feed inputs one by one from the left. Imagine we feed it like 1 and then after 0 and then 1 and so on. Or we can feed it from the right, again 1, 0, 1, something like that. Or we can feed it the data all at the same time. If we have 4-bit in parallel, we can do all at once. Now we also have the parallel outputs that you can see on the top. And these two are the clear and the clock. If we set the clear at 0, you can see the clear is connected to the clear of all the flip-flops. And it will clear the register and it will put 0 at all the register, or it will reset all the registers. Now, what type of flip-flop are we using here? the D flip-flop or the data flip-flop. The D flip-flop is capable of storing 1 bit of data, and we are using 4 multiplexers, 4x1 multiplexers. Their select points are all tied together. So S1, S2 is connected to the first one, and it's the second one. And so every select is connected to each other. It could be selected at the same time. Now, let's see when we change S1 and S2, what does the system do? Or S0, S1. So the select points control the mode of the register. If it's 0, 0, then we would have no change, meaning we would keep the data, maintain the data, it's good, and it works like a memory. It's normal memory. If S0 is 1 and S1 is 0, then we would have a shift right, meaning it will shift 1 to the right, all the digits to the right. If it's 1, 0, it will shift 1 to the left. All the bits would shift 1 to the left. And if we put 1 and 1 for the select points, we would have a parallel load, meaning we would upload all the data and the input into our flip-flops, or in other words, into our register. Now that we learned about registers, again, registers, we can have shift right and shift left, and I solved some practice problems. I'm going to do another one just for you to have a reminder of what a shift register does. Imagine we have a shift right or system, and the bits in the 4-bit registers are 1, 0, 1, 0. If I shift 1 bit to the right, what would the output be? Thank you. 0, 1, 0, 1. Everything would shift 1 bit to the right. The 0 would fall out. This would be a vacant, and we would replace it with a 0. So the first one on the left. And this is not a circular register, by the way. This is an open. And I would explain about circular registers as well. Circular register, you would take that 0 that fall out at the end and put it back on the left. Now, a different type of sequential logic circuits is a counter. A counter is technically built out of a register, and it's capable of counting up or counting down. Okay. So a counter, as mentioned, is basically a register that goes through a prescribed sequence of states upon the application of input pulses. The input pulses are usually clock pulses. Can you give me one example of a counter? One example that we use a counter, I'm sorry. One application of a counter. You all have it with you. A digital clock. A digital clock is a counter, and it goes to 60 or 59, 0 to 59, then goes back, okay, when you counting the seconds. Stopwatch, all of that is a counter. And the frequency for that, if you have a stopwatch, it could be milliseconds, microseconds, and for a normal watch, the frequency is just 1 hertz. And by changing that clock, you're adding to the number, so it goes 1, 2, 3 seconds, 4, so 159, then it goes back to 0. And then it changes them. So digital clock, a very good example of a counter. We use a digital counter and counters a lot, especially in microcontrollers, microprocessors. When you reach the circuit design, you would see this a lot. One example of this that I could give is, imagine we have an ultrasonic sensor. One is a transmitter, another one is a receiver. I give this example a lot. The way that an ultrasonic distance measurement system works, it sends a sound wave. So it has a speaker, and at the moment that it sends that sound wave, it has a counter or a stopwatch that starts counting. So for example, it counts 1 second, 2 seconds, and then it goes and comes back. The speed of the sound is 330 meters per second. So if it takes 2 seconds for it to go back and forth, it had traveled 660 meters. We divide it in half because we want to find the transmission when it goes and comes back. So the distance between the sensor and the wall is going to be 330 meters, for example. So this is a type of counter that we use. There are different ICs that are made for counters, and you can use that you don't need to build a counter from ground up. And there are different ICs that, for example, 4-bit or 8-bit counters that we can use. Now, one example is an in-bit binary counter that counts in binary from 0 to 2 in the power of n minus 1. So if for example, we have a 3-bit counter system, it will count between 0 and 2 in the power of 3, which is 8 minus 1, which is 7. So it will count from 0, 0, 0 to 1, 1, 1, and then it will go back to 0, 0, 0. Okay. So this is a normal binary counter. Then we have a ripple counters, which the flip-flop output transition serves as a pulse to trigger other flip-flops. And then we have the synchronous counters, which the flip-flops receive the same common clock as the pulse. The ripple counter is like a serial counter. The synchronous counter, the clocks are in parallel. The ripple counter is like a domino. When you put dominoes, it has like a domino effect. The first one is activated. The output of the first one triggers the clock of the second one, and so on. The synchronous counter is, as I mentioned, it's like these shades that you can, close and open all at the same time. This is an example of a 3-bit binary ripple counter. And the idea behind this is to connect the output of one flip-flop to the C input of the next high-order flip-flop. We need complementing flip-flops. We can use a T flip-flop to obtain complementing F flip-flop, complementing flip-flops, or we can use a JK flip-flop, where we have to tie the inputs together. Or we can use a D flip-flop with complement output connected to the D input. On the left, you can see the truth table. The 3-bit binary ripple counter, as I mentioned, starts from 0, goes to 7, and goes back to 0. So 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, down to 1, 1, 1, and then it goes back to 0, 0, 0. This picture shows the schematic of a 4-bit ripple counter. Now you can see from this ripple counter that the output of the first flip-flop, and by the way, the left one is a ripple counter using a T flip-flop. The right one is using a D flip-flop. So again, this is a T flip-flop, and the right one is a D flip-flop. So in these type of ripple counters, the output of the first one controls the clock of the second one. The output of the second one controls the clock of the third one, and the output of the third one controls the clock of the fourth one. So if the first flip-flop is not activated, the second one would not be activated. If the second one is not activated, the third one won't be. So if the first one is not activated, all the flip-flops coming after that would not be activated at all. And you can see it has like a cascading effect. Same thing for the D flip-flop as well, with a small tweak. In a D flip-flop, again, the output of the first flip-flop controls the clock of the second one, or the higher order one. And by the way, these are the lowest order to the highest order. So A0, A1, A2, and A3. If we write it, it's going to be like this: A0, A1, A2, and A3, which is the higher order. And so on. So the output of the third one also controls the clock of the fourth one. Now, what is the input of the ripple counter? The input is usually just a single clock or count, what we say. So a single bit, we just activate the clock of the first one, and it exactly as I mentioned, like having a domino, series of dominoes. If I push the first one, what happens? It topples the second one and the third one. I'm not very good at drawing, and then a fourth one, and so on. So unless we have the first one activated, we don't have the third one and second one, and so on. So imagine you put a bunch of dominoes, and the first push that we give it, it's actually our first count or the first clock. So we give it a clock and it starts counting. And it will continue counting until we reset it, for example. And how do we reset or clear it? Using the clear button. So when we push the clear, it would activate all the resets. All the resets and these flip-flops are connected, tied together. And as soon as we push that clear, all the outputs would be 0. It's going to reset, and it's going to start over counting. And it's the same thing on a stopwatch. On a stopwatch, you have a reset, you push it, everything goes back to 0. Now, for a 4-bit binary ripple counter, we can also use, as mentioned, a JK flip-flop as well. And in a JK flip-flop, we just need to tie J and K together, which technically creates another T flip-flop. Now here, in the previous slide, we had a 3-bit. Now we have a 4-bit binary ripple counter. Now for this 4-bit, suppose the current state is 1100. What would the next state be? So A0 goes from 0 to 1. A1 goes from 0 to 1. So A0 would be 1, 1. A2 goes from 1 to 0, and A3 goes to 1. What is 1100 equal to in decimal? 12. What is 1011 equal to? 11. What is it equal? 1 plus 2 plus 8. It will be what? 11. So we went from 12 to 11. Is this a countdown counter or a count up? Countdown. So this is a countdown. So the next state would be 1011, which is 11. So it's counting down, countdown, 12, 11, 10, 9, and so on. So a binary ripple counter or any ripple counter could be count down or count up. For the register, we could have a right shift register and left shift register. For a counter, we can have a count up and a count down counter. Now, we learned a binary ripple counter. We can use a ripple counter to create a BCD ripple counter as well. And a BCD number, do you remember what numbers were BCD numbers? So BCD was a 4-digit binary, and it went from 000, 0001, 0010, all the way to 1000. So it was between 0, decimal, 1, 2, to 9. Do you remember this? So BCD was between 0 and 9. And what happened after 9? No, that was a hexadecimal. BCD from 9 went back to 0. BCD went from 9 back to 0. It technically shows a 1-digit decimal, a BCD. So we went from 101 to 000. If you remember, when we added 2 BCD numbers and the result was greater than 9, well, what did we do? We added 6 to it because we wanted to go back. We wanted to circle back to 000. Now, here you can see a BCD ripple counter. It starts from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, and back to 0. So it's a circle counter. For a, if this was a binary counter, it will go from 0 to what? 4-bit, 0 to 2 in the power of 4 minus 1, which is? Yes, perfect. So it's 0 to 15. If it was a 4-bit binary, but this is a 4-bit BCD. So it goes from 0 to 9. Is it clear? Is it clear, or do you want me to go? Okay. So the state transitions for a BCD ripple counter, it starts from 0, 0, 0, 0, which is 0, then goes to 1, 2, 3, 4, 5, 6, 7, 8, and 9. By the way, this is 9. And then it goes back to 0. And I'm writing the decimal over here. For a 4-bit binary, it goes from 0 to 15 back to 0. BCD 0 to 9 back to 0. Now a BCD ripple counter with a JK flip-flop, again, we need to tie the J and K together. Technically, it's a T flip-flop. And because it's a ripple counter, the output of the first flip-flop, JK flip-flop, is connected to the clock of the second one, and so on. And the second one to the third one, and the third one to the fourth one, but with a small caveat, small difference between them. Because obviously we can't go over 1, 0, 1, 0, 1. The system will look like this. You would have an AND gate connected to the last J flip-flop. And the K flip-flop and J flip-flop for the last one are not connected together. Now, for a multi-digit BCD counter, we can have multiple of these BCD counters connected to each other. And for here, we can have, how many digits do we have? We have a 3-digit BCD counter, and each BCD counter is four digits. So it's going to be 12-digit system. And we already solved one that has multiple, BCD digits and how we add them and so on. The reason that I put this here is that these BCD counters come in a single IC, so you don't need to connect those flip-flops together to create a BCD counter. It already comes with a different IC that you just need to put the clocks and the inputs and the outputs, which are the BCD numbers. Now, the ones that we studied so far are the ripple counters. Now, we want to dive into the synchronous counters. A synchronous counter, all of them have a common clock, meaning you would have a single clock and all the clocks are tied together. That clock triggers all the flip-flops simultaneously. If T is equal to 0 or J and K are equal to 0, the flip-flop does not change the state. If T is 1 or J and K are 1, then the flip-flop does change the state. The design procedure is so simple, no need for going through sequential logic design process. A0 is always complemented. A1 is complemented when A0 is 1, and A2 is complemented when A0 is 1 and A1 is 1, and so on. So A3 would be complemented when A0 is 1, A1 is 1, and A2 is 1, for example. And if it's 0, then it won't be complemented. This is a schematic of a 4-bit binary synchronous counter. So if in the exam I show you a counter and I ask what type of counter is it, the way to determine if it's a synchronous or a ripple counter is to check the clocks. If all the clocks are connected together like this one, if all of them are tied together, connected to a central clock, it's going to be a synchronous counter. If the clock is connected to the previous output, that's going to be a ripple counter. Now again, the only input that we have here is the count enable, and then the output is connected to the AND and the next inputs. The J and K inputs are tied together. You can also replace this with the T flip-flop. And the outputs are A0, A1, A2, and A3. The polarity of the clock is not essential here. And finally, we get an output which is connected to the AND gate and goes to the next stage, which is going to be, technically, it's going to be the carry for the next stage if we want to connect another IC to this. Now we have up or down binary counters. So in terms of the configuration, we have two types of counters. We have ripple counter and synchronous counter. And in terms of their application, we have count up or count down. Okay, so 4 different categories you can say. So a up-down binary counter, when counting downwards, the least significant bit is always complemented with each clock pulse. A bit in any other position is complemented if all lower significant bits are equal to 0. For example, if we have 0, 1, 0, 0, the next state would be 0, 0, 1, 1. What is 0, 1, 0, 0 equal to? 4, thank you. What is 0, 0, 1, 1? 3. So it's a countdown, as you can see. And what is 1, 1, 0, 0 equal to? Again, 1, 0, 1, 1, 11. So a countdown system. So the first thing that we would do is we will complement A0, as you can see, and then all lower significant bits, if all lower significant bits are also equal to 0, we would complement them. And this is an up-down binary counter. It has an extra pin. Up here we have extra pins, which determines if this is a up counter or a down counter. And by selecting these up and down, giving 1 and 0 to 1 or 0 and 1, we can create an up counter or a down counter. It's exactly similar to the previous one, again, as mentioned, but the only difference is we have added these inputs. You can see that the clocks are tied together. So this is a synchronous up-down binary counter. It's made out of, this is a, how many bits is it? Three bits. It's a 3-bit. We have 3 flip-flops, 3 outputs, A0, A1, and A2. So it's a 3-bit up-down binary counter. A 3-bit synchronous up-down binary counter. Now, that one was a binary counter. We can also create one for a BCD synchronous counter as well. So in this situation, it's better to apply the sequential circuit design procedure. If the present state is 0, 0, 0, 0, which is 0, the next state would be 0, 0, 0, 1, which is 1. And then if it's 1, next one would be 2. If it's 2, next one would be 3, and so on, 4, 5, 6, 7, 8, and 9, and back to 0. Now the Y output would be 0 until we reach the end when we want to go back, circle back to 0. And the flip-flop outputs are equal to the next state. That we had. Now, a synchronous BCD counter, the flip-flop input equation, T1 is equal to 1, T2 is equal to A8 prime A1, T4 is A2 A1, T8 is A8 A1, A4 A2 A1. And the output equation, Y would be 8 A8, A1. Where did we get these equations? I will show you the flip-flops, but we get it. There are two ways to get this, by the way. We can go from the circuit back to the equations, or we can go from the equations using a K-map to the circuits, which I would explain as well. In this system, we have 4 T flip-flops, 4 2-input AND gates, 1 OR gates, and 1 inverter. Again, this is the circuit for a counter with a BCD counter with, and it's very similar to this actually, just a small difference between this. This is a binary counter with parallel load, by the way. BCD counter, I would add it. It's just a small difference in connecting the J and K flip-flops. Now for a binary counter with parallel load, again, we have the count, the load, D0, D1, D2, and the clock and the clear. And we can load this counter. The previous counters, we cannot give it an input, predetermined input. We can't say, oh, start from counting from 4, for example. We can just reset it to start from 0. For a parallel load counter, we can say, for example, start from 232, start from 300. But for a normal counter, we can just reset it to start from 0. Now, in a binary parallel load counter, we have different functions. If clear is 0, it will clear everything to 0. If clear is 1, then we will load the inputs. If clear is 1, the clock is coming, load is 0, and count is 1, it will count up. If clear is 1, the clock came then, load is 0, and count is 0, it's going to have a no change or act like a register. Now, other types of counters, we have a ring counter, which is a circular counter. And the timing signals control the sequence of operations in a digital system. A ring counter is a circular shift register with only one flip-flop being set at any particular time. All others are cleared. So what it does, imagine we have 4 students sitting on a table, and I give them a cup, and I tell them to move this cup around, or I give you one piece of paper, just one, and I tell you to, give it to your friends. And then, so what it does, for example, if I give a 1 over here, and all of these are zeros, the next step, the 1 moves, so this would be 0, 1, 0, 0. And for the next step, it's going to be 0, 0, 1, 0. Next one is going to be 0, 0, 1. So it moves that bit, the initial value, it moves that 1 digit along. So you can see what happens. In the first sequence, T0 is 1, and the rest of them are 0. Then T1, so when T0 is 1, T1 is 0, T2 is 0, and T3 is 0. So I have 1, 0, 0, 0 for the first sequence. And in the next sequence, it's 0, 1, 0, 0. And the next sequence is going to be 0, 0, 1, 0. And finally, it's going to be 0, 0, 0, 1. And then it's going to start all over again. So it moves this 1 bit along. This is called a ring counter. Now, what is the benefit of a ring counter? It's if you have an error in the system, so for example, if you have 2 1s, you would definitely know that there is an error in the counter. And if it moves, skips a bit, you can easily catch that as well. So for error detection, a ring counter is pretty good. But it has its own limitation. If you want to count from 1 to 100, you need to have 100 flip-flops, because 1 bit is in 1 flip-flop, so you need to have 100 flip-flops. But if you want to build a 0 to 100 counter using a binary counter, how many flip-flops do you need? 2 to the power of 5 is 32, 2 to the power of 6, 2 to the power of 7. So 2 to the power of 7, or a 7-bit counter, would be enough. For this, you need 100-bit or 100 flip-flops. Okay, so that's the limitation that we have in a ring counter. Now, in a ring counter, to generate 2 in the power of time signals and overcome that limitation, we need a shift register with 2 in the power of n flip-flops, which as mentioned, if you need like 100 of them, it's going to be 100 of those flip-flops. Or we can construct the ring counter with a binary counter and a decoder. So another way to overcome this problem is using a decoder. Now the cost, 2 flip-flop, 2 to 4 line decoder. And for a general case, we needed n flip-flops, and n to 2 in the power of n line coders, long decoders, and 2 in the power of n input AND gates. So you can see we can significantly reduce the number of gates that we need. Now, another type of counter that we have is called the Johnson counter. So a Johnson counter is a k-bit ring counter that can generate k distinguishable states. The number of states can be doubled if the shift register is connected as switch tail ring counter. Now this figure shows the Johnson counter, and you can see we have 4 D flip-flops, and we have a circular connection that connects T prime from the last one to D of the first one. Is this a synchronous counter or is it a ripple counter? Synchronous. So if in the exam I ask if there's a question that what type of counter is a Johnson counter? Is it a synchronous ripple counter? It's going to be a synchronous counter. Now, a Johnson counter has a decoding circuit as follows. Now we can have 8 outputs, so S0, S1, S2, S3, S4, S5, S6, and S7 with 8 AND gates and the 4 D flip-flops that we had. And a Johnson counter looks like this. We have used states and we have unused states. In a Johnson counter, only 1 bit changes at a time. Okay, so we go from 0, 0, 0, 0 to 1, 0, 0, 0. So only 1 bit changes, and then another bit, the second bit changes, then another bit. And you can see that what happens at each point, just 1 bit is changing. Again, it's very good for error detection, and it's very good in power as well. Why? Because if I had a binary counter, if I wanted to go, for example, from 1, 1, 1, 1 back to 0, 0, 0, 0, I needed to change all 4 bits, and it will. But here, I go from 1, 1, 1, just changing 1 bit, and then another bit, and then another bit, and finally going back. So it's going to significantly reduce the energy consumption, and we are easily able to find the error, because if you go from one count to another and suddenly 2 bits change, we know that there is a problem, because you're only allowed to change 1 bit at a time in a sequence. But this creates another problem. The problem is that we have 4 bits. If we have 4 bits, how many different numbers do we have? 2 in the power of 4 is equal to what? 16. 0 and 5. How many numbers do we have in a Johnson? 1, 2, 3, 4, 5, 6, 7, 8. So we use 8 digits in a 4-bit digit, and we don't use the other 8. Okay, so we have 8 used states and 8 unused states in a Johnson counter when it's a 4-bit counter. So if, again, in the exam, question is, how many used states do we have in a Johnson counter? We have 8 used and 8 unused system. And these, which are in black, shows the used states, and the red ones show the unused states. So the used states, you can see that start from 0, 0, 0. The next one is 1, 0, 0. Then 1, 0, 0 goes to 1, 1, 0, 0. 1, 1, 0, 0 goes to 1, 1, 1, 0. And you can see just one bit changes at a time. So here we just change this bit. Here we just change this bit. Here we just change this bit. 0 went to 1. And for the next one, we changed this bit, this bit, this bit, and so on. And the last one as well. Sorry, the last one is, yeah, this 1, 1, 0, 0, 1, 0, change, then 1, 1, change, and so on. Which you can see. And this is the unused situation, and this is the used situation. Now, if we want to draw the K-map for a Johnson counter, and we can do that for this exact thing for BCD counter to be able to find its equations and functions and also the circuits. X is going to be equal to T prime here. Y is going to be equal to X. And Z is going to be equal to XY plus YZ. And T is going to be equal to Z if we solve all of that. And for the unused states in a counter, the circuit will look like this. We would have 4 flip-flops, D flip-flops, an OR gate, and 1 AND gate. And the connections will look like this. Again, X was equal to T prime, Y is X, Z is X plus Y, and Y plus YZ. Z is XY plus YZ, and T is equal to Z. Now, if we want to draw the diagram, the state diagram, it's going to look like this. The blue ones show the used states in a Johnson counter, and the red and the purple shows the unused. So we have 8 used and 8 unused situations in the counter. So the unused situation, I can see at each point 2 of the bits are changing. So I'm going from 1010 to 1101. So at least 2 are changing. 2, sometimes 3 are changing. And that creates problem. Again, waste of energy, and for error detection, would have some problems. Okay. Now we will continue with the reason that I added the shift registers, because registers are very important in the class. And I wanted to make sure that I have time to finish the registers so I can get back to the state reduction and how we do the state reduction, which would, again, that part was much more important. So what was the state reduction that we had? State reduction was when we had these state diagrams that we did for flip-flops. And by the way, this applies to registers and counters as well. And as you remember, we had the sequential circuits. And again, this is both for registers, counters, all of that. And using these state diagrams, we could determine the next state. And as you remember, the left one was the, let me go back to the state diagram itself so you would remember. The circle shows the AB, the left shows the input, and the right, for example, showed the output. And based on the table that we had, we could determine the next state. Now, we can use this state diagram in different methods like the Mealy and Moore to be able to simplify our state diagram, therefore to be able to simplify our sequential logic circuit. For a combinational logic circuit, we usually did that through a K-map. For a sequential logic gate, one way to do it is to use the state reduction and assignments. So the state reduction reduces it's a reduction on the number of flip-flops and the number of gates. A reduction in the number of states may result in a reduction in the number of flip-flops. So this is a method for simplifying our sequential logic circuits. Again, for combinational logic or combinational logic circuits and functions, we use Boolean algebra and K-map. For sequential, we can use the state reduction system. An example state diagram is shown here. We have A, B, C, D, E, F, and G. And if we show the state and the input and output, again, we have A. And if I do 0 and 0, the input and output, by the way, input, and we have the output. So 0 and 0, we will go back to A. So 0 and 0 goes back to A. Then I can go from A to B, B to C, C to D, D to E, E to F, F to F, for example, F to G, G to F, and G to A. Now, if I want to go, for example, from A to B, what is my input when I'm going from A to B? Input is 1, output is 0. So if I do 1 and 0, I'm going A to B. What if the input and outputs are 0 and 0? 0 and 0, I'm going from B to C. From B to C. And if the input outputs is 1 and 0, 1 and 0, I'm going from C to D. And I'm also going from B to D as well. Both of them, same input, 1 and 0, I'm going B and C to D. And then again, from D to E, if I have 0, 0, I'm going from D to E. If I have 1 and 1, I'm going from E to F. Again, 1 and 1, I have F to F. And then 0, 0 goes from F to G. And 1, 1 goes G to F. 0, 0 goes F to G. And 0, 0 goes for G. 0, 0 goes to A. Now, for state reduction, we only import the input output. We put only the input and output. These are important. The rest isn't important, the states. We would have two circuits which are equivalent. They have identical outputs for all input sequences. The number of state is not important again. Only the input and outputs are important. Now, what we would do, we would create the table or the state table. For equivalent states, two states are said to be equivalent when for each member of the set of inputs, they give the exact same output and send the circuit to the same state or to an equivalent state. So here, which one gives us the same output? Again, this is our diagram on the right, and we have the table. Again, each member of the set of inputs, they give exactly the same output and send the circuit to the same state or the to an equivalent state as well. Which ones look similar? Can you give me one example by looking at this? I just want you to look at it so you can think for a few minutes. Perfect. Perfect. Yes. Yes. Perfect. Yeah, that's correct. Yep. Now, if I draw the table like this, E is equal to G when we remove G, and D would be equal to F when we remove F. Again, D to E to F, and then F to E to F. So you can see that we can reduce that, the ones that are circled with red, and we will be left with this. We have A, B, C, D, E, and A, C, A, E, A is going to be our next state, or B, D, 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 D is going to be our next state when X is 0 and X is equal to 1. Now the states, we will reorganize it like this. We have A, B, C, D, E, D, D, E, D, E, A, and the outputs are going to be based on the input outputs that we have from the table. And the system has been reduced to this. So we went from this to this. What have we erased? We have erased F and G. You can see that F and G are erased. We don't have them anymore. We just have A, B, C, D, E. Now, the checking of each pair of states for possible equivalence can be done systematically using implication table. The unused states are treated as don't care condition or fewer combination, which results in fewer combinational gates. So this is the reduced state diagram of the previous one. Now the implication table, the state reduction, you can read faster than I do. The state reduction procedure for completely specified state table is based on the algorithm that two states in a state table can be combined into one if they can be shown to be equivalent. There are occasions when a pair of states do not have the same next states, but nonetheless go to equivalent next state. Consider the following state table. Again, we have A, C, B for the next state, and then B to DA, and C to AD, and D to BD. AB implies CD. You can see, AB implies CD. And CD imply A and B. You can see C and D by A. Both pairs of states are equivalent, and therefore A and B are equivalent, as well as C and D. The checking of each pair of states for possible equivalence in a table with a large number of states can be done systematically by means of an implication table. This is a chart that consists of squares, one for every possible pair of states, that provides spaces for listing any possible implied states. Consider the following state table. We have A, B, C, D, E, F, G, same thing as the first one. And for that, we have the next states. Let me bring that up. By the way, this is a B. And for that, the implication would look like this. We have A, B, C, D, E, F on the x-axis, and on the y-axis, we have G, F, E, D, C, and B. So A, B, C, D, E, F, G. And then we have B, C, D, E, F, G. So shifted one to the right. Now, in this implication table, on the left side along the vertical are listed all the states defined in the state table except the last. And across the bottom horizontally are listed all the states except the last. The states that are not equivalent are marked with an X in the corresponding square, whereas their equivalence is recorded with a tick sign. Some of these squares have entries of implied states that must be further investigated to determine whether they are equivalent or not. The step-by-step procedure of filling in the square is as follows. First, we will place a cross in any squares corresponding to a pair of states whose outputs are not equal for every input. Second, we will enter in the remaining squares the pairs of states that are implied by the pair of states representing the squares. We do that by starting from the top square in the left column and going down, and then proceeding with the next column to the right. Then we will make successive passes through the table to determine whether any additional squares should be marked with X. A square in the table is crossed out if it contains at least one implied pair that is not equivalent. And finally, all the squares that have no crosses are recorded with check marks. The equivalent states are A, B, DE, DG, and EG. We now combine pairs of states into larger groups of equivalent states. The last three pairs can be combined into sets of three equivalent states, DG, because each one of the states in the group is equivalent to the other two. The final partition of these states consists of the equivalent states found from the implication table, together with all the remaining states in the state table that are not equivalent to any other states. So we would have A and B, C, D, and E, and G, and F. The reduced states table will look like this. It's a little blurry. I would replace it. And I think it's enough for today. I will continue with the state assignment in the next class, and I will solve some practice problems. It may seem a little confusing till I solve some practice problems, and I will solve some practice problems in the next class, so you would get familiar with the state assignment and the state reduction, and the implication table as well. So that's it for today's class. Thank you so much, and I'll see you after Thanksgiving.